Hi, good afternoon, and welcome to the ZP Developer Zone. So we like to do this webinar really talking about translation of academic research into products and technologies. We do this once a month, and really without any further delay, I'll sort of jump into it. So this is welcome to the academic webinar. As I say, we're really kind of interested at ZP about translating academic research actually into products. Now, there is always a caveat to that statement, which is what kind of funding is in place, because any kind of effort in terms of academic let's say some kind of funding. But with that said, I will dive into it. Now I do have some technologies in front of me, so I will be doing a couple of demonstrations about how we, at least at ZP, think that academic research can be translated into products and let's say services as well. So we're about creating impact. We're about fundamentally electrochemical sensors. So I kind of have a few electrochemical sensors that I'll probably be using this afternoon in this discussion. And I'll also, and I'll be doing some demonstrations of those. Talk about biosensors a bit. A lot of what we do at ZP is electroanalytical chemistry. So I think one of the futures is the rapid measurement of analytes in complex samples. And I will give a couple of examples of that. And in fact, what I'll do now is I'll immediately kind of come off the conversation and actually just kind of do a few demonstrations of the technology stack that we do actually have at Zimmer Peacock. So I'll stop sharing for a second because it makes the screen a little bit bigger. I'll jump into this camera here. And I just want to kind of show you that at ZP, I have an instrument in front of me here. We call it Sense It All. This is a way of it's a couple of things really. It's a potentiostat, and it's a way of translating academic research into real products. Now, first of all, what I'll do is I'll just demonstrate it as a potentiostat. So I'll take a something like I'll take a screen printed electrode from ZP, which I'm doing. I'll put it onto the instrument. Now, what you'll notice about this particular instrument is it doesn't look like a normal scientific instrument. And in fact, it's actually controlled by an app on my phone. So what I'm just going to do is I'm just going to scan over to not linear sweep voltammetry, but I'll go to cyclic voltammetry. Now, the reason I did that is because we don't want people to get stuck in a R&D mindset with equipment that kind of looks like R&D equipment. It really holds them in a sort of, in a place where they can't actually then translate the academic research. What I'm going to do is I'm just going to get a little drop of this, and I'll just do a quick live demonstration of this. Now, what I'll do is a very classical kind of, piece of electrochemistry, but then I will sort of use that classical piece of electrochemistry to sort of tell, to sort of give a story. So what I'll do is I'll take that sample, I'll put that on like that, which I have done. Now what I'm just going to do is I'm just going to go up to here and say, okay, this is my smartphone. It's in Bluetooth connection with this particular device. I'm going to go ferricyanide, let me just spell it right. Ferricyanide. Sorry about that. Cyanide. It's just me being quick. 5 millimolar. Right. I'll go back here. I'll go continue. So now it looks like a bit like I've got these settings. So this won't all be about electroanalytical chemistry. I'm going to do some real world samples in a minute as well. So in a bit, you'll actually see me start testing this material, for example, which is a can of Red Bull. But stick with me for a second while I just do this experiment, because I want to sort of say, the start of any kind of translation of academic research is actually a start with a kind of, a certain sort of type of experiment. And I will hit start here, and that is now off gathering the cyclic voltammogram. So as it goes, now what I'll also be doing then is showing you that there's something quite good about this system, that's actually what we call cloud enabled. So not only can I run experiments and see the progression of those experiments on my phone. I can also then analyze the data up in the cloud as well. So once that's completed, I will move to the cloud. So it now says upload complete. So I'm just going to do a quick sharing of my screen. Have a quick look here. And I will share here. So here it goes. So when it says upload complete, what it means is all the data actually got sent to a cloud system called Julie. So when it says upload complete, it actually means no, we didn't just do the experiment. The data also went to the cloud as well. And so I've got the data up here. This was a quick experiment that I just did where I was actually looking at ferricyanide. But what's kind of interesting about this particular system is most let's say lab experiments kind of finish at this stage where you've kind of got raw signal. But what's very different about this system is that I can actually come in here. I can take a quick look at settings. I can I'll find the peak position. I think the peak position was somewhere about 200 plus or minus 100. I'll just have a quick look and see what that looks like. So what I'm now doing is showing you that the data's gone to the cloud, and actually I can start doing some settings in that cloud, and actually so I can see that I've just missed the peak here. So I need to shift my analysis window over to about 400. So let me just do that real quick, and then we can have another look. Because what it shows you is that where most academic research finishes, it finishes at the raw signal. But with this system, it's quite clever that actually, there we are, I've picked up the 400 there. So we can actually take this a bit further and actually turn raw signal actually into concentration with just a few. Now, I'm not expecting end users to do this, but I'm just showing you how you can. I'll just try an arbitrary 10 in here. I'll put the intercept at 0. What I'm doing here is just making up the calibration. I should really formally do this in a more kind of formal manner, but it allows me to, every time I do the change, where does it go? Yeah, here we go. So I can see here that it's found the peak height. I put in some calibration factors, but they were wrong because I got 39 millimolar here. But I'll just change. You can see if I change these numbers. Let's just try 0.1 for a second. Actually, I'll try 100. This is that I've just found a very good strategy of being able to kind of start off with 10s, because then you can kind of in a sort of and now what I'm doing, see, is now I've come to 10. I've got 3.9. I know that the real answer is I didn't come to 10, so I came to 100. Let me just try 120 for a second and see what that does to the number. And then I'll do a quick summary of, that was a very quick flash 3.222. Let me just try 90 for a second. I just want to see if I'm going in the right direction. Here it goes. No, I went in the wrong direction. So I'll just do 80 and then I'll leave it at that. Because what I want to do is I want to demonstrate how that we can actually do a normal lab experiment, not just leave it at raw signal, but actually bring it from raw signal. There we are. I got to about 4.88. Now the truth is it's actually 5 millimolar. But that's just now what I can do now is send that result back to the phone. So I'm going to do a second demonstration, but with a real world sample. So I'll stop sharing for a second. I will, you can see my screen nice and big again. I will take away that screen printed electrode, and I'll actually bring in one of our caffeine sensors. So far, I just demonstrated, okay, I took ferricyanide, I did a CV on it, and then I was actually able to show you how I could turn that peak height in that CV and cyclic voltammogram into a real number quite quickly. Now, what I'm going to do now is I'm just going to grab a quick sample of Red Bull. I'll just open this can up. Right, so I've got this. This is a kind of a real world application. So I'll take the can. I will put the Red Bull in like that. I'm going to do everything that's sort of effectively live in front of you, just to kind of give you a sense of, you know, what we can do, let's say. So what I'll do now is I'll take some buffer. I'll also do that live in front of you as well. So it's a real world sample. I've got right. So I've got 100 microliters of the sample like that. So there's the Red Bull, 100 microliters. Put that to the side. Then I'll take 100 microliters of the buffer, which I'll do. So I've got these two, whoopsie daisy, that really, yeah, I did take. Now I'll shake those two guys together. Nice thing about this kind of sample is it's very quick to prepare. I did that. And then what I'll do is I'll take 50 microliters of that final sample. Put it onto the sensor like that. Now what I'm going to do now is I'm just going to show you that this system, every time somebody comes up with a new assay, we're able to create a new QR code. So this is a different assay, same instrument. I'm just going to scan that QR code. Now I've got a new modality. This one is much more sort of customer friendly, because you've got to think about what's holding back academic research is that people are serving up technology from labs that looks nothing like a real product. But this is actually the potentiostat. I've just changed the mode of this potentiostat into a real world application just by using a QR code, which we can quite easily reprogram these systems, and now it's gathering the data in real time on that caffeine sensor. I can see the peak for caffeine just there now. So that will process the data. It's given me the result. That result is absolutely perfect. The Red Bull content is 0.03% by mass of caffeine, and that translates to 0.3 to the nearest decimal point, 0.3 milligrams per gram, and it's exactly what I've got here. Again, it's actually sent the data to the cloud. So I'm just going to share my screen with you for a second. We come up to here. And so now, rather than doing just a cyclic voltammogram on, a sort of known chemical, let's say, now we're actually analyzing a real world sample, and you'll be able to see you'll be able to see more of the workflow. So if I go into here, which I am going, and so here's the caffeine. What's really nice is if you're working with students or real world people, I can see the name of the file, I can see the date, I can see the time, I can see the operator, I can see the raw signal. Just out of interest, this is actually square wave voltammetry, what we're doing here. And you can see the way actually the system has already found that peak. It's measured the peak height and converted the peak height into milligrams per gram. And the milligrams per gram, 0.318, was sent back to the phone. So what I've demonstrated here is the ability to either use this instrument as almost like a pure R&D instrument, or actually you can either as a pure R&D instrument, or actually as what we call a minimally viable product as well, that you can actually use it to go into the real world. So I'll just show you some of that kind of R&D functionality. So we can do amperometry, we can do open circuit potentiometry, we can do EIS, impedance spectroscopy, linear sweep voltammetry, cyclic voltammetry, or square wave voltammetry. Or once let's say the academic or the group that's using this has developed a real assay, then we can go, I'll just go and scan over here, turn it into a real world application, like how much capsaicin is in a chili sample, which we're kind of fairly well known for. So what I'll now do is just share my screen with you and go through a few more slides. So you can but I just wanted to kind of jump into that very quickly to just set the stage that we're not talking about theoreticals here. We're actually talking about something that we've generally developed. So we call it Sense-It-All. It's a potentiostat. It works with, in particular, ZP screen printed electrodes, and it means that you go from a scientific paper, and most scientific papers finish at TRL3, technology readiness level number 3. If you're using this technology, then you can actually turn it into a minimally viable product as well using the technology platform. So that was a demo. Now, the current situation, I'll discuss what's happening in academia at the moment. What I've demonstrated to you just now was actually point of need testing, and that's, I think, electrochemistry and electroanalytical science is one of the best applications for its point of need testing. I'll talk about screen printed electrodes. The biggest problem, or one of the biggest problems in the world of commercialization of academic research in my world, is actually reproducible screen printed electrodes. And I think that's one of the parts that ZP is really ahead of the game of, is actually reproducibility. I'm showing you something that's really unique, a cloud-enabled potentiostat. Every time you do an experiment, that data is going straight to the cloud. And once it's in the cloud, we've got a very strong analytical platform to actually turn raw signal into concentration. No more laptops, smartphones only, no menus. You saw that I was using QR codes. And it allows the translation of academic research. Most academic research, as I say, finishes at TRL3. Technology readiness level number 3, as defined by NASA, just means a proof of principle in the lab. And that's exactly where most science stops. Whereas with this technology, we were able to take square wave voltammetry, and we were able to use it to make a analysis for Red Bull. We're able to take cyclic voltammetry, and we'll make an analysis for capsaicin in chili products. So I'll show that as well shortly. And then I'll just do a summary at the end. So the current situation is there's lots of scientific papers every year being produced. This one's from the University of Oxford, and they all follow the same format: an introduction, or sorry, title, introduction, some kind of mechanism, maybe experimental section, some results section, and maybe a conclusion. And that paper from University of Oxford is not unique. This is one from UWE, University of West of England. Again, title, abstract, introduction, materials. Here they are using screen printed electrodes, data, conclusion. And in my world, you've got lots of competing journals all publishing these kind of papers. And in fact, I was talking to a researcher from University, or the Manchester Metropolitan University, and he told me that they estimated there's 25,000 papers like that per annum. The problem that we're trying to solve at ZP is there are 25,000 papers per annum just in our little niche of the world, and they are not being translated into actual products, and therefore society is not actually benefiting from them. And that's a real problem, because actually I think that, especially in the next few years, there's going to be a real crunch from on academia, from government, because the funding is drying up, and governments want to see a real return on investment on all these papers. So there's going to be a lot more pressure for that sort of impact part. Now, with that University of Oxford paper, that came out 2018, and it would reside effectively as another paper, but in fact what ZP were able to do was actually take that original paper and actually turn it into a product. So what I'm going to do is I'm just going to stop sharing for 1 second, just so you can see my screen a little bit easier, and I will just change cameras for a second. So let's take that wrong camera. Let's take that idea of that paper from the University of Oxford, and we will translate it into a real product. So let me take a sample like this, or let me take a real world sample. Let me put in the sample here. Now, what you'll notice is all these samples are very kind of real world. They're also very, I don't want to say dirty, but they're complex samples, because the good thing about electrochemistry as a scientific method is it's really able to deal very nicely with complex samples. So what I'll now do as well is I'm just going to take some buffer. And this is something that we ship with this when we launched it as a product. This is something that we also ship with it as well. Now, don't forget, I'm actually using the same instrument here. So the same instrument that I've shown, I did a cyclic voltammogram of ferricyanide. It's the same instrument then I showed that can do amperometry and open circuit potentiometry, EIS, linear street voltammetry, square wave voltammetry, cyclic voltammetry. It's the same instrument as before. And I then did the caffeine measurement on it as well. And now I'm going to do another analysis. I'm just going to take 100 microliters of this. I just want to get a slightly wider pipette, which I will do. And then I'll take 100 microliters there and show you how I'll analyze that. I come in, I take my 100 microliters, which I've done. I'm now going to grab my, I've got my buffer there, which is great. I will take a sample of that buffer. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, so now I've prepared my sample. I'll just show you my sample quickly. So I've now prepared my sample. What I'm going to do is I'm actually in this one, I'm going to show you that sometimes we have to compromise. I'm going to have I'm going to just quickly do a quick vortex on that sample, because I've really got a molecule called capsaicin that's slightly in the sort of solid phase, and I want to get it out of the solid phase into the liquid phase. So I just give it a quick vortex. That will certainly homogenize everything. I take the sensor off, but I now need to grab one of my chili sensors. So I just grab one of those. You will notice that, there we go. Now I bring in the chili sensor like that. Something that makes all of this work is actually the quality that we put into manufacturing, because what you'll notice is I'm not doing any calibration. And that's not because I'm being wrong in some ways. The reason that you often see calibration or normalization of data in scientific papers is because the screen printed electrodes are actually irreproducible. But because we produce such a reproducible screen printed electrode or sensors, then we actually don't have that problem. So what I'm going to do now is I'm just going to go into the app. I'm going to give this a name so I can find it. TAB 10.1. That will help me find that in a minute. Come back here. Now I'm going to put 50 microliters. The other benefit of electrochemistry is it doesn't require much sample. Drops of blood are perfectly fine. I'll go continue. I'll just go start, and off it goes. So it's now doing, actually in this particular case, we're doing cyclic voltammetry. We can see the data coming in real time, and you will see very shortly that it's given me a perfect answer. So it's given me, and you can see the way we're serving this back to the client. So we're sort of saying Scoville heat units 2210, and it also says upload complete. So let's go and look at my screen again. Upload complete means, yep, it's gone to Julie. So I'm sharing this Julie system that I'm actually sharing. I'm showing you here. I mean, this is 10 years. This has been 10 years in development. A tool like this doesn't just come from essentially nowhere. So I'll click on it, and then the data. So don't forget, all of this has gone live to the cloud. All the time I've been talking and doing these demonstrations, all of this has been going live to the cloud. So I can see, the voltammetry, nice. You can see the way it's found the peak here, for example, and it's again turned the peak peak height into chemical concentration. So I'll just go to here, and so I'll sort of summarize a little bit and then move on with some more slides. So what I'm trying to demonstrate is that academic research gets stuck. Why does it get stuck? Well, in part, the instruments are scientific instruments, but real world people do not want scientific instruments. They want easy to use instruments. They don't even want to call them instruments. They want to call them things like meters and stuff like that. But what we've done is we've taken a potentiostat that's both a potentiostat and is able to do real world samples. We've put a big effort into making really reproducible electrodes. Something that's holding back so much academic research is actually these electrodes that people are using are really irreproducible. It means that they for the same concentration, they'll get different signals. They think that they can't work out what the problem is, and the problem is it's actually the screen printed electrodes. What made those assays so quick and easy was I did no calibration. But that it takes a lot of effort at ZP to make sure that these electrodes are reproducible. Saw me put the electrodes on the meter. You saw me put the sample on the meter, either ferricyanide, the Red Bull, or the Tabasco sauce. You saw me able to go between different methodologies or different targets using QR codes. What happens is that when I press, essentially continue, the app sends the instructions to the potentiostat, and the potentiostat actually gives the raw data back to the app, and the app sent it to a cloud system called Julie, where we actually processed the data and sent the result back to the app. Back to the app. So you actually get a result. So the end user is not ending up looking at cyclic voltammetry. The end user actually gets something that's meaningful to them. In this particular case, the concentration of capsaicin. Now, the reason that we can do all of this is fundamentally big problem in academic research. In my world of electrochemical biosensor development is the electrodes. They're not reproducible. People, correctly so, go for the lowest price or the easiest available, but what they don't realize is that it's then holding back their research. So it was always the intention at Zimmer and Peacock that from almost day one that what we were trying to do is create a suite of technologies that would help move science from the lab into the real world. And we've realized that we have to demonstrate that that is the case. And so, we've actually now have a system for analyzing caffeine. We have a system for analyzing capsaicin in chili samples. And then we use these technologies, or academia are adopting these technologies to actually get their assays actually into the real world. Because this system, it ticks one box. It looks like a real product already. So in fact, getting doctors and nurses to adopt it and use it in their in the R&D, it's another step to actually become a medical instrument, but it makes it easier to translate the science out of the lab and actually into the real world. And part of that technology stack is actually our screen printed electrodes as well. Now, we like to do this webinar. Most of what I've done this afternoon is actually demonstrations. The screen printed electrodes, the potentiostat, the app, and the cloud system. If you have any questions, you have my email, but I would say don't hesitate to reach out to us, and I thank you very much. Okay, have a good rest of the day. Take care. Bye-bye.